Okay, so we're looking at SAT worksheet 211, geometry. The geometry on the SAT is predominantly triangles and circles. So we'll cover those in detail. I'll show you specifically what the test expects you to know for each. What I will say at the start of this video is I've picked out 7 problems to cover from past tests. I do think this video will run a little bit on the long side, so close to or maybe even above 30 minutes. By all means, if you understand the concept, just fast forward, move. I'd rather err on the side of giving too much information than too little. I want to make sure that you're in a good place to do this worksheet and understand the concepts. But also feel free to kind of go at your own speed and speed things up if you want to. Okay, so that being said, let's just get right into it. So it's imperative when it comes to triangles that you know your special right triangles and your Pythagorean triplets. The former isn't really taught over here in the UK. I find most students don't know this. They tend to reach for their calculator and use trigonometry to figure out the proportions. Pythagorean triplets are pretty well known. Both of these come in handy on the test. You're almost guaranteed to see triangles that employ either the special right triangles or the Pythagorean triplets, and it'll save you time, and sometimes you'll even be precluded from getting a problem right if you don't know these. So we'll look at those in detail. And then on the second half of the worksheet, we'll look at circles. The third half is just other geometry problems. We won't cover those in this video, but by all means, they're in the packet, so you can practice them. So let's talk about triangles first. I know you know the 3 angles of a triangle add up to 180. If you think about it, for any shape, every time you add a side, you add another 180 degrees. So a square, rectangle, any 4-sided figure is 360 degrees. A pentagon is 540 degrees, hexagon 720, and so on. The equation for that is n being your sides minus 2 times 180. That gets you the sum of all interior angles. And if it's a regular shape, meaning that all sides and interior angles are the same, then you can just divide it by the number of interior angles you have to figure out how much each one is. For instance, if you're looking at a regular hexagon, where all, my drawing's not great, but where all these sides are the same, so the angles are all the same, what you do is you do 180, or in this case 6 minus 2, divided by 6. And we're looking at 4 times 180, so that's 720. 720 divided by 6 is going to get us 120 for every side. Anyway, let's get back to triangles. So you need to know what an isosceles triangle is. 2 sides are equal, so 2 angles are equal. You need to know an equilateral triangle. All of this is basic stuff that I'm sure you would have covered for GCSEs. But here's something that you need to know that you probably don't know. The test gives you this in the equations, but you really just need to know this yourself. You need to know the proportions of a 45-45-90 triangle and a 30-60-90 triangle. Those are the 2 special right triangles. And you see I put a big star next to these. So if you have a 45-45-90, and excuse the measurement being outside, it's supposed to be inside, but if you have a 45-45-90 triangle, the proportions are across from the 45s are your base side, so your smallest side, so XX, and then across from the hypotenuse is x root 2. Or sorry, across from the 90 degrees, your hypotenuse is x root 2. So if this were 5 and this were 5, this would simply just be 5 root 2. Cool. 30-60-90, this comes up even more often, and you really want to know this. For 30-60-90, across from the smallest side is your base side, x. I'll just make up that it's 5. Across from the 60 is 5 root 3. Root 3 is like 1.7 something, so it's 5 times 1.7 something. And then your biggest side, because it's across from your largest angle, is going to be 2x, or 10. Okay. So how does this commonly come up? Well, one is if you ever put a diagonal across a square, immediately that cuts the corners into 45-degree angles. So you get a 45-45-90 triangle. I guess we're seeing kind of the bottom half of this square here. And this triangle, if we know this to be 4, Well, 4 is equivalent to x root 2. So that means that quite simply, x is equivalent to 4 root 2. And if you want to rationalize it, so multiply the top and bottom by root 2 to rationalize it, you'd get 4 root 2 over 2 is equivalent to x. So finally, x is 2 root 2. So if they want to know what is the area of this square, it would just be 2 root 2 times 2 root 2 divided by a half. And it's interesting because I can see here I left it as 4 over root 2. I left it at this point because I knew I was going to multiply them. But 4 over root 2 times 4 over root 2 gets you 16 over 2, so you get an area of 8. A lot of times on an equilateral triangle, it can be turned into a 30, 60, 90. So if you needed to get the area of an equilateral triangle, there's a formula for it, but I imagine most of you guys won't want to memorize this formula. You can look at it if you want to, but I'm not going to bother to explain it in this video. It's more just if you want kind of extra credit. But anyway, if we're given this equilateral triangle and we want to know the area, we drop an altitude like we did here, and immediately it creates a 30, 60, 90 triangle. Well, across from the 90 is 6. Across from the 30 is going to be half of the hypotenuse, right? That's going to be your x side. I'll kind of scroll up, or no, you don't have it here. I'll just draw it. Right, if you have a 30, 60, 90, it's going to be x root 3, 2x. So if 2x is 6, then we know this is 3, and we know this is 3 root 3. We want to get the area of this entire thing, so it's going to be 6 is our base, right? Because it's going to be 2 3s. So 6 times 3 root 3 divided by 2. And that's going to get us 18 root 3 divided by 2, which is going to get us 9 root 3. Okay, so that's just something to be aware of. Area of a triangle we know is 1/2 base times height. Just know that if you get a weird looking triangle like this, that can be your base, but you're not going to use, if they give you that this is 10 and this is 6, let's say, your area is not going to be 10 times 6 divided by 2, because 6 is not your straight up height, it's your slant. It's on a slant. So you'd have to drop an altitude and somehow figure out what h is. So it wouldn't be 10 times 6 divided by 2. It would be 10 times h divided by 2. So just something to be aware of. Okay. Pythagorean triplets. These you really want to know. You want to know the first two. These are the first two sets of integers that will give you a right triangle. Okay. So if you look at this set, 3 squared is 9. 4 squared is 16. 5 squared is 25. That's your first Pythagorean triplet. 5 squared is 25. 12 squared is 144. Add them together, you get what 13 squared is, which is 169. So you kind of just want to know these proportions for right triangles. And you also want to know that you can get similar triangles that would have the same proportions. So I may know 3, 4, 5, but if I'm told this is 6 and this is 10, before going for Pythagorean theorem, I can just quickly write in that that's 8. And you'll see how that comes in handy as we go over the test problems. Okay, so I picked 4 out for us to do. Okay, this hourglass problem is a favorite of mine. It gets a lot of students, but it doesn't need to get you. So this is what we do on the hourglass problem. What we do is, if you think about it, if you have 2 parallel lines, okay, and I'll just extend these ever so slightly, you would know that the opposite interior angles are the same. So if I were to draw another one like this, I'll extend that, so you would know that these opposite interior angles are the same. So it's the same thing with this hourglass. So if you think about it, angle Q is the same as angle S, and angle P is going to be the same as angle T. And we know that because it tells us that PQ and ST are parallel. I probably should have read the problem first. So it gives us, you can pause the video and take a second to read the problem. It gives us the measurements that they've labeled, and it also tells us that these two lines are parallel. Okay, so anyway, because they have two angles in common, they actually have three angles in common. Because they have three angles in common, we know that these are similar triangles. So we just need to figure out the scale factor if we're going to figure out the length of RT. So if you think about it, so we want RT. I'll just put a question mark next to that. So what we know is this. We know that the small one is 5 when the large one is 6 with the proportional sides. So we have to figure out what side do we care about on the small one in order to figure out RT on the large one. Well, now that we've correctly labeled the angles, we know we don't care about 8, we care about 7, because Q and S are the same angles, so across from Q is going to be proportional to across from S. So essentially, we know the small is 7, and if we cross multiply, we get 32, not 32, oof, math, 42 equals 5 RT. RT meaning just this side of the question mark. So divide 42 by 5, and that should get us just slightly over 8, probably 8.4. And it does. Okay, perfect. So that's that one solved. On these hourglass problems, just make sure you label your angles, because it's really common to assume that 8 is proportional to this, but it's not. 7 is proportional to this. Okay. Ooh, this should look very familiar. All right, so we have triangle ABC above, and it wants to know what is the length of AD. So it wants to know from here to here. So first things first, this looks eerily like it could be a 30, 60, 90 triangle. In fact, we know that this has to be 30 degrees here. And the fact that this has to be 30 degrees here means that this has to be 60 degrees up top, which means we have two 60 degrees. So this has to be 60 degrees. So this is an equilateral triangle. Okay. You could reach for your calculator and start to do this through trigonometry if that's what feels comfortable, but I'm going to get it much faster. Why? Because I just know my 30, 60, 90 proportions. So I'm going to encourage you to know them too. This is our 2x side. The height is our x root 3 side. So across from the 30 is going to be our x side. So across from the 30 is going to be 6. We know that, so because of that, and because these are similar triangles, these two, we know that this is going to be 6 as well. Cool. All right. So anyway, and if you're curious, just for extra credit, this side would be 6 root 3. If for some reason we had to figure out the area, the height would be 6 root 3. Okay. 2 more on triangles. These next 2 are a step up. This was one of the last ones on a test right here. If you want a challenge, pause it, try the problem out. Sorry. See if you can get the problem before, yeah, just see if you can get it on your own. But if not, we're going to continue on here. Okay. So Thomas is making a sign in the shape of a regular hexagon. Regular means all sides and angles are the same. So each one of these sides is 4. All of these angles are the same. All right. So what we did at the way beginning of this video is about to come in handy, which you will cut out from a regular sheet of metal as shown in the figure above. What is the sum of the areas of the 4 triangles that will be removed? So he wants the sum of the areas of these 4 triangles in red. Okay. So what do we know? Well, we know that this side is 4. We know that this is a right angle. Gosh, it would really be helpful if we just had one more angle, because really we need the base and we need the height. So we're kind of stuck if we can't get the base and the height. But here's what we do know. We do know that this is a hexagon. A hexagon, all of the interior angles are going to add up to 720. How do I know that? Well, I know a triangle is 180. I know a 4-side figure is 360. 5-sided figure is 540. So a 6-sided figure is going to be 720. So I just add 180 for every side. Again, the equation is n minus 2 times 180. That gets you the sum of all the interior angles, and n represents sides. So if we divide this by n, and again, this was at the way beginning of the video. If you remember, I put in 6. So 180 times 4 gets us 720. 720 divided by 6, right, because this is 6 and this is 6. 720 divided by 6 gets us 120. Why is that a big deal? Well, I'll show you why it's a big deal. If this is 120 degrees right here, then we know this is 60 degrees right here because we have a straight line. If this is 120 degrees right here, we know each one of these are 30. We have a 30, 60, 90 triangle. Okay, so before you go to reach for your calculator, you can, and you can try to use trigonometry to figure it out if that's your preferred method. But I would encourage you just to realize, wait a minute, across from the 90 is 4, so our base is going to be 2, and across from the 60 is going to be 2 root 3. So the area of one of these triangles is going to be 1/2 base times height, so 2 times 2 root 3 divided by 2. So the area of one of these triangles is going to be 2 root 3. We have 4 of them, so that's going to be 8 root 3. Cool. What you'll notice, if you notice this is a 30, 60, 90 triangle early on, then you'll actually hedge your bets towards answer A, because root 3 should almost always signal to you that you're looking at a 30, 60, 90 triangle somewhere, if you have root 3 in the answer choice. Root 2 should tip you off that you're looking at a 45, 45, 90. So just something to look out for. If you see root 3 or root 2 in the answers, it's almost hinting to you that you should expect to be able to create a 30, 60, 90 or a 45, 45, 90. Okay. Last triangle problem, and then we'll do a few circle ones. Yeah, I thought I could fit it. Almost. Sorry, a little bit of an eye test here. Okay. So this problem says, the figure above is the floor plan drawn by an architect for a small concert hall. The stage has a depth of 8. So stage goes back 8 meters. And 2 walls, each of length 10. So these are the walls of the stage. If the seating portion of the hall has an area of 180 square meters, what is the value of x? So we know this is 180. And so let's kind of see what we know from here. So if you remember, I told you that it's really helpful to know your Pythagorean triplets, your 3, 4, 5s, and your 5, 12, 13s, the first 2 of them. Well, if you look at this one, we have a right triangle. Well, I wanted to do that in red. There we go. We have a right triangle. This is 10. This is 8. Well, if you think about it, this is just double 4. This is just double 5. So this one's going to be double 3. So this one's going to be 6 here. A 6, 8, 10, which is just a doubled 3, 4, 5 triangle. So we know that 6. And yeah, you could have used Pythagorean theorem, but I think this is easier to just know 3, 4, 5. So if we know both of these are 6, then we know that this side is going to be 12 in total. If we know that side is 12 in total, 12 times x, right, because it's a rectangle, gets us 180. 180 divided by 12 is going to get us 15. How did I know that? Well, I know 10 times 12 is 120, and half of 120 is 60, so you add another 60 to get to 180. So it's going to be 10 of these, and then another half of 10, or another 5 of these. If that didn't really make sense, that's okay. You just grab your calculator. Or you can do it by hand. You use long division. But anyway, this is 15. Okay. So let's look at circles. We have a couple of concepts to quickly cover, and then we will look at 3 circle problems. I'll show you kind of the 3 most popular circle problems. Okay, so you need to know a circle is 360 degrees. You need to know the area for the circumference and the area of a circle. So 2 pi r circumference, or pi diameter. Some really smart Greek mathematician figured out that, hey, if I can just figure out this, then if I multiply it by pi, or about 3.14, I'll get this. So he figured out that the proportion of the diameter to the whole circumference of the circle was by a factor of 3.14 or pi. All right, but anyway, you need to know those. They're given on the test, but it's just helpful to know. A big thing is you need to know that the circle is 360 degrees, because a lot of times what they'll do is they may give you the length of this arc. So they may tell you the length of this arc is, I don't know, 2 pi, I'm making it up. And they may tell you that your radius is, let's say, 10. And they're going to want to know, what is this angle? Well, the way you do this, and we'll do a later problem just like this, but the way you do this is you'd realize, okay, wait a minute, my entire circumference is going to be 20 pi, right? Because it's 2 pi r. So my entire circumference is 20 pi. This small portion is 2 pi of 20 pi. In other words, it's 1/10 of the whole thing. And I need to know that my whole circle is 360 degrees, right? The whole circumference is 20 pi. The whole circle is 360 degrees. So this is kind of the circumference part. This part is the degrees part of the ratio. Kind of divide it like that. But anyway, scale factor, we just want 1/10 of 360. So we know immediately, okay, based off of the numbers I made up, that has to be 36 degrees. And we'll do a problem like this in a moment. Whenever you draw 2 radii from the center and then connect it with a chord, that creates an isosceles triangle. Any line tangent to the circle, meaning just touching it, if you draw a radii to that point that just touches, that creates 90 degrees. If you have a diameter and then you draw to any point anywhere on the circle, that will create a 90-degree angle. And again, feel free to review these later. And then the last big one of the circle properties is that if you create an arc towards the center and then you just go beyond the center anywhere, then that cuts the angle in half. So if this is 120, that's 60. Okay. So let's put this to work. And again, I encourage you to kind of look through those on your own time to make sure you feel comfortable with those. But let's do this problem first. This is similar to the one I explained a second ago. So it says segments OA and OB are radii. So these segments are going to be the same. Of the semicircle above arc AB, so this arc, I'll do it in yellow, is going to have a length of 3 pi. Okay? And it says OA is 5. And wants to know, what is the value of X? Okay, so fair enough. What we do is we figure out the entire circumference of the circle. So we know that circumference equals 2 pi r. In this case, our r is 5. So the entire circumference is going to be 10 pi. So what do we know? Well, if we look at circumference of the circle versus degrees, what we know is we know that 3 pi is the part, right? The arc that we care about, this AB, is 3 pi. We know that the whole is 10 pi, right? It's a part to whole ratio. Okay, and what do we know about degrees? Well, we always know that the whole circle is 360 degrees. So all we need to figure out here is how many degrees is X. Well, I'd first simplify this to just 3 over 10. So we have 3 over 10 equals X over 360. Okay. If we, no calculator. Okay. So we got to kind of be clever here. But if we do 3 times 360, that's going to get us 1080, but I'll do it by hand. 3 times 0, 0. 3 times 6 is 18. Put the 8 here. Put the 1 here. I had to put the 0 there. 3 times 3 is 9, plus 1, 10, so 1080. So essentially, what we have is 1080 is equal to 10x. Divide by 10, x is going to equal 108. Awesome. All right, 2 more circle problems to take a look at. 35, not just a circle problem, but a triangle problem to boot. So there's a special deal today at the SAT store. It's 2 for the price of 1. And I'll show you how cool this problem is. It was one of the last problems on a test. So it's one of the harder problems on section 3, which is a non-calculator section of the SAT. So it says, in the figure above, the circle has center A, and the line segment CB is tangent to the circle. So we know this to be 90 degrees because this is a radii, and then this line is tangent. If AB is 1, so A to B is 1, this whole thing, and CB is 0.8, what is the length of the diameter of the circle? So you could use Pythagorean theorem, but you don't have a calculator, it's going to be kind of nasty. Or you could realize, wait a minute, this is like a 10, 8, 6 situation, or a 3, 4, 5 situation, or in this specific case, we're looking at 0.6, 0.8, and 1.0. So we know this to be 0.6, which means we know the diameter to be 1.2. Do not take the bait on A. A is in front of D, and it's wrong because it's tempting, and a lot of students will just circle it and think they have the answer. Always take a second moment to reread what the question is asking before you pick your answer. It'd be a shame to know how to do all of this and then give the point back to the test anyway. Okay, last problem we're going to look at. This one. Ooh, looks very interesting, doesn't it? So let's see what we're looking. And again, as always, you can pause it, try to see if you can get it without me. Be more than happy if you're able to. But if you're not sure how to go about it, then just continue on. And if you want to try it, then just unpause the video when you're done to check your answer. But anyway, here we go. In the figure above, O is the center of the circle. Segment BC is tangent. Okay, so we get a 90-degree angle again there to the circle at B. And A lies on segment OC. And it tells us that OB, so this radius, and O and AC are the same, and it tells us that those are both 6. So, and then it wants to know the area of the shaded region. I want to see if I missed anything here. OB is equal to AC, and I think I have everything here. Oh, yeah. This is what I was why I had a brain freeze. This is going to be 6 as well, because this is a radii as well. So hopefully you took my word for it earlier. I'm just going to redraw this triangle right here. If this is 6 and this is 12, a light bulb should go off in your brain, and you should go, wait a minute. 6, 12, 6 root 3. 30, 60, 90. And that's why you really want to have the proportion down tight. Because if you're trying to do it through trig, if you're trying to do it another way, you just may not get there. I'm not saying you can't, I'm just saying I would recommend it this way. Okay, so anyway, we're going to know what is the area of the shaded region. So what we're going to do is we are going to figure out the area of the triangle, this triangle, and then we're going to subtract this sliver of the circle. So we're kind of putting all of our knowledge to use, or both our circle and triangle knowledge to use on this problem. So how are we going to figure out the area of the triangle? Well, we already have the base, we already have the height, right? Because it's on a 90-degree angle. So we're going to multiply them by one another and get 36 root 3. And then we're going to divide that by 2 because it's a triangle. So we know the area of the entire triangle to be 18 root 3. What we want to subtract is this sliver. We want to take this sliver out. So here's what we do know. Because we know this is a 30, 60, 90, oh my God, that makes our life so much easier, because we know the area of the circle to be pi r squared. Well, we know our r to be 6, so the area of the circle is going to be 36 pi. Well, 60 degrees is, so we know 60 is to 360, right? If we're talking about part to whole in degrees. You know, 60 is to 360 as whatever this sliver is in area is. So I'll just call it S for sliver. Whatever this sliver of the pi is to 36 pi. Well, hopefully you see here that we're just looking at kind of dividing by 10 and then adding pi. I mean, you could cross multiply and everything, but really the sliver is going to be 6 pi. So we have 18 root 3 minus 6 pi. Interestingly enough, if you get the area of the triangle and you're not sure where to go from there, then you already have a 50% chance because you know it's going to be 18 root 3. Or conversely, if you're able to get the sliver, what the sliver is, but you don't figure out the triangle, well, you also have a 50% chance because if you know the sliver is 6 pi, then you know that gets rid of A and C. So even if you can't get the whole thing, you can always kind of increase your chances or odds of getting it right. But 39 is a perfect example of why you really want to be tight with the 30, 60, 90 on triangles and how you want to understand how to set up ratios or proportions with circles out of 360 degrees. Okay, hopefully everything in this video has made sense. If not, then maybe watch a part of it again or go somewhere else because I probably didn't do a good job explaining it then. But anyway, good luck with the practice. Good luck with this worksheet. If you can get the circles and triangles down and what we went over, it will go a long way in making your test day significantly easier. Okay, bye.